Hello students, I am Praveen Kumar from ABS Engineering College, Ghaziabad. In today's video, we are going to discuss about single-phase induction motor. Like three-phase induction motor, the single-phase induction motor also has two major components. Stationary part is known as stator and rotating part is known as rotor. The single-phase induction motor mainly consists of squirrel cage rotor, but the difference is on the stator side. Here, as the name suggests, the stator consists of a single phase winding. And when single phase AC supply is given to this single phase winding of stator, a pulsating magnetic field is developed. By pulsating means this alternating magnetic field is neither constant in magnitude nor in direction. So, such type of field is not capable of developing any starting torque, and that's why single phase induction motors are not self-starting in nature. The behavior of single phase induction motors can also be explained on the basis of double revolving field theory, which states that any pulsating magnetic field can be resolved into two synchronously rotating magnetic fields of constant magnitude having magnitude half of the pulsating field but revolving in opposite directions. Here we can see that this pulsating field of magnitude phi m can be resolved into two synchronously rotating magnetic field. One is rotating in clockwise direction, other one is rotating in anti-clockwise direction, and magnitude of both these field is half of the pulsating field. So here the resultant field at theta is equal to 0 degree. Both the fields are exactly opposite to each other. That's why resultant is 0. At theta 90 degree, both these fields are acting in vertically upward direction. So at this instant, the value of flux is maximum phi. So in this manner, double field theory states that there are two synchronously rotating magnetic fields in single phase induction motors. And with the help of these two synchronously rotating magnetic fields, there are two torque developed in the rotor. One torque tries to rotate this motor in forward direction, which is developed due to forward field, and other torque is developed due to backward field and which tries to rotate the motor in backward direction. As long as this rotor of single phase induction motor is at rest, the torque corresponding to the forward field as well as the torque corresponding to the backward field, both these torques are equal and opposite. So the resultant torque, as long as the rotor of single phase induction motor is at rest, both the torque are equal and opposite, and the resultant torque is 0. But as the rotor of single phase induction motor is shifted from this rest position in any direction, we can see that there is resultant torque is available. And as rotor is shifted from this rest position, in the influence of this resultant torque, the rotor can accelerate, or we can say this motor can operate. So this is how we apply double revolving field theory on single phase induction motor. Now, the various mechanism with which we shift the rotor of single phase induction motor from this rest position is known as the methods of starting. And the various methods of starting of single phase induction motors are: first method is resistance start motor, second is capacitor start motor, third one is permanent capacitor motor, and the fourth one is two value capacitor motor. Now we will discuss all these methods one by one. So first of all, this is a resistance start motor. In this motor, basically what we do, along with the main winding of the stator, a additional winding is also placed in the stator, which is known as starting or auxiliary winding. The main difference between main and auxiliary winding is where the main winding is highly inductive in nature, whereas the starting winding is resistance is kept high, whereas the reactance of starting or auxiliary winding is kept low. And here is a centrifugal switch is also connected in the auxiliary or starting. Due to different resistance properties, here we can see that the the current flowing in main winding is lags behind applied voltage by a very large angle, as this main winding is highly inductive in nature, whereas the starting or auxiliary winding have a very high resistance. So due to highly resistive nature, the current flowing in the auxiliary or starting winding is almost in phase with the applied voltage. So due to different phase currents, here we see that the current in main winding and auxiliary winding have a in-between displacement, and due to this phase displacement, we can see that the flux developed by the main winding and starting winding tries to develop a two-phase system. But this developed two-phase system is not balanced. Reason is this internal phase displacement angle alpha in this case is hardly around 40 degrees. So as the two currents are hardly displaced from each other by 40 degree, means the flux is developed by these two windings. They tries to develop a two-phase system, but that developed two-phase system is not balanced, or we can say a very weak magnitude of rotating magnetic field is developed. But this weak rotating magnetic field is sufficient for this rotor to develop its starting torque like three-phase induction motor. As the rotor starts rotating and gains its speed around 60 to 70% of rated speed. At that particular level, the centrifugal switch operates, and what it does, it disconnect the auxiliary winding from the circuit. So while running condition, the only main winding is present in the circuit, and this auxiliary or starting winding is disconnected with the help of centrifugal switch. Here, sorry, Here we can see these slip torque characteristics of the single phase induction motor, and this is the point where the centrifugal switch operates, and we can see the sudden dip in the motor torque. So initially, when both these windings are present, this much value of starting torque is available. At this particular point, centrifugal switch disconnect the auxiliary winding, and beyond this point, motor runs only on main winding. So this is how a resistance start motor. The main drawback of this motor is very low starting torque, as the developed two-phase system is not balanced. Here, this phase displacement angle is only around 40 degrees. One more thing, this motor has very low power factor during running condition. So to overcome these drawbacks, the another method is developed, which is capacitor start motor. As the name suggests, in this type of motors, a capacitor is installed in the auxiliary winding. This capacitor, when connected in the auxiliary winding, it makes auxiliary current to lead with the applied voltage, and in this case, this internal phase displacement angle alpha is increased to 80 to 85 degrees. So almost a balanced two-phase system is developed in capacitor starts motor. And once in this balanced two-phase system, once this rotor develops the starting torque and motor starts running at a speed around 60 to 70% of rated speed, then this centrifugal operates and disconnect this auxiliary winding. Here, the capacitor used in these winding is electrolyte capacitor, which is present in the circuit for very short duration. In capacitor start motor, the drawback of poor starting torque is eliminated, but here still the problem of poor running characteristics exist. So just to get better running characteristics, the next type of motor is developed, which, which is the permanent capacitor motor. In permanent capacitor motors, the main winding and auxiliary winding both are permanently present in the stator, and there is no centrifugal switch present in this motor. So it means this motor for entire duration it runs on main as well as auxiliary winding. In this type of motor, a different type of capacitor is used, and this capacitor usually we represent it as CR, known as running capacitor. This running capacitor is paper insulated capacitors, and for higher ratings, it is filled with oil. So these type of capacitors are costly, but they can be connected in the circuit for longer durations, and if they permanently kept in the circuit, they can improve the running characteristics also. So this permanent capacitor motor, its one common application is in our ceiling fans. This type of motor is used. The drawback of this permanent capacitor motor is that a single capacitor is utilized for starting as well as running characteristics. So neither the optimum starting characteristics is obtained nor the optimum running characteristics is obtained, as the single capacitor is used for both the purposes. So just a advancement of this permanent capacitor motor, this two value capacitor motor is developed. Here, this is the main winding. In auxiliary winding, we can see that there are two capacitor. One is starting capacitor, which is electrolyte capacitor, and other one is running capacitor, which is paper capacitor. Both are connected with the help of centrifugal switch. So when motor is in its starting phase, both these capacitance CS and CR, both these capacitors are connected in parallel, and a net capacitance of CS plus CR, it is utilized for starting the motor. As the rotor starts running to the 60 to 70% of rated speed, at that time centrifugal switch operates and it disconnects the starting capacitor, which is the electrolyte capacitor. And the running characteristics are improved with this help of running capacitor. So in this manner, this by using two value capacitor motor, we can get optimum starting as well as running condition. So these are the different methods with which we can start single phase induction motor. I hope you enjoyed watching this video. These are the references which are used while making this video. So I hope the concept of single phase induction motor is clear through this video. Thank you for watching this video.